So I guess it's time. Should we resume? Okay. Thanks again, everyone. So we're going to resume the session, and we're going to switch gears from the cathode to the anode. And we are actually really glad to have Professor Stefano Passerini. So just briefly, Professor Passerini got his PhD in Roma, in La Sapienza, before to move to the US for quite some time. And after that, he came back to Italy and is now, correct me if I'm wrong, since more than 10 or 15 years in Germany. And he's professor of physical chemistry and director at the Elmos Institute of Ulm and at the Karlsruhe Institute for Technology. And as well, we also know him as the editor-in-chief from Journal of Power Sources. So we are actually really glad to have him and really glad to listen to him discussing about graphite and silicon anodes. The floor is yours, Stefano.
Thank you, Alexis, and thanks for inviting me to give this presentation, and I'm very glad to do it. So, initially I thought I was the first speaker, and then I prepared a kind of introduction on lithium-ion batteries. But anyway, I won't spend much time, but definitely, I mean, the whole story about lithium-ion batteries started about 40 years ago now. With Michel, and then he developed with Whittingham, proposing LiTS2 and demonstrating cells. Then actually, one of my former PhD supervisor, I just talked with him yesterday, he's doing pretty well, demonstrated the first Rongying cell in 1980, and then there was the huge development we know about lithium-ion batteries. The anode, definitely, graphite definitely played an extremely important role in the development of lithium-ion. I mean, it was not always used. The first commercial, I mean, at the beginning, graphite had, there were several problems with for lithium insertion because it tended, pure graphite tended to co-intercalate also the solvent molecules, and this resulted in the destruction of the graphite structure. So actually the first commercial lithium-ion cells used hardened, especially soft carbons. But finally in the 1990s, it was identified the EC could prevent the exfoliation of graphite, and then in 1994, the lithium-ion batteries using graphite electrodes were commercialized. Since then, we are mostly using steel graphite. There is not much of a difference. On the other end, at the beginning of the, about 10 years ago, let's say, the introduction of silicon into the anode has also started, and right now, actually, some commercial cells contains a small amount of silicon. But we will see this in more details later. So as I said, graphite was really a key material for lithium-ion batteries. We all know what is the structure of graphite. There are these graphene layers stacked in a zigzag configuration. The interlayer forces or interaction in graphite, we all know that graphite can be used for pencils, are very weak, and this is actually making graphite the perfect, I would say, intercalation host, because the layers can very easily adjust to host different ions, and especially lithium ions. So how does it work? A little bit on the mechanism. It has been demonstrated that actually the lithium storage in graphite occurs through this, what is called the staging mechanism. So lithium is not stored uniformly between all layers, but it tends to actually fill few layers once in a while, and then the more lithium we put in, the more layers are filled. there was a mechanism proposed by Rudolph and Hoffman in which practically they proposed that layers were filled, and then at a certain point another layer was filled, as you can see in this sketch here. Nonetheless, this was obviously a simple picture because it is very tough to believe that at a certain point all the lithium ions could move from this layer to the previous one, going from stage 4 to stage 3, for example, and then the same going to stage 2. And what is actually happening in reality was well described by the model of Doma and Herold, in which in practice lithium it's more or less entering in all layers, but it's locating in different positions, so that what we see if we are looking only at a small area like this area, we see the same picture as here. But in this way, it is obviously much easier to understand how it can happen that other layers are filled. Don't forget, never forget, the lithium can never go across the layer. It can only enter from the edge and migrate inside. What does this mean? I mean, this staging mechanism is very well seen when we do the lithiation and delithiation of graphite, and we record the potential or the voltage, depending if we have 3 electrodes or 2 electrode cell. What we see are these typical steps, okay, which occur when a certain staging happens. Okay, so when we have a small amount of lithium, we have a rather high voltage versus the lithium plating potential, and then we hit a second region where we have the stage 3, and then we the following region stage 2, and then at the very end we have the stage 1 where all layers are full with lithium. And we can very well observe these plateaus, especially if we use low or moderate current rates.
Stefano?
Yes.
Stefano? I'm really sorry to interrupt. I think your presentation is frozen, unfortunately.
Oh, but it's not frozen on my screen. Where was it frozen? Where did it freeze?
We are still on the staging mechanism, indeed. So I should have warned you before.
Slide number 5.
Yes.
I can stop sharing and restart. Sorry. Okay. Can you see it moving now?
No, we are still waiting for the slides to arrive.
This is strange because I see it on my screen, and I see I will switch off my camera. Maybe this helps.
Yes, may help for the bandwidth.
Can you see it now?
No, it's still loading.
Oof, that's a big problem. I'm very sorry for this. I have a full connection. I'm inside the office, so there shouldn't be any problem.
Can you stop sharing and try again, just to see if it's helping?
That's exactly what I'm doing. And
okay.
Show. Okay. Technology. Share screen, PowerPoint, share, and start. Is it better now?
Same, it's still loading. Okay, now we see. Try to move.
Can you see it?
Okay. Yes.
Okay. Then, okay, then I was here, I guess. I mean, from the
yes.
How do we see this stage mechanism in practice? Well, first, we obviously can do X-ray investigation, but we can get this information also just measuring the potential upon lithium insertion in graphite. And what we see are these typical steps, which are typical of multi-phase or two-phase processes. And these occur obviously at different potentials. And the more the graphite is lithiated, so the more channels between the layers or planes between the layers are filled, the lower is the lithium insertion potential. You also notice at the beginning there is a very different behavior, let's say, from the rest of the discharge and charge curve. And actually, this is something very important that happens in graphite, and it's what is called the first cycle irreversible capacity. There is this certain amount of charge which is flown into the cell at the beginning that goes specifically into the solid electrolyte interface formation. Okay, this is needed. When it's well done, it occurs only in the very first cycle, and in the following cycles, a very reversible behavior is observed with only the typical staging mechanism occurring for the lithium insertion and the insertion. What is this SCI? I mean, how does it occur, and what is the role? Okay, so if we consider we are charging a lithium-ion cell, that means we are forcing electrons into the negative electrode. Okay, these electrons obviously reach the interface with the electrolyte. A series of reaction, usually very rather irreversible at the beginning, reaction occur, leading to the formation of an SCI, this solid electrolyte interface, which is, we will see it later, what is it? I mean, naturally. But the great advantage of this SCI is that it is actually blocking the transfer of electron from the electrode to the electrolyte. So it's blocking the reaction after some time occurring at the interface, but it's still enabling the passage of lithium ion, which then leads to the charge, let's say, of the lithium ion cell. Okay. Another great advantage, which I forgot to highlight, is that the presence of the SCI prevents the solvent co-intercalation. So only lithium ions can go through the SCI and enter into the graphite structure, and these avoid the delamination of the graphite structure. So this solid electrolyte interface, it is actually what makes lithium-ion batteries working. It's extremely important, okay? But it also, there are also some, it forms during, hopefully only the first cycle, but anyway, just during the first few cycles, maybe 2, maximum 3. 1 is the best. And it should also occur with the minimum amount of side reactions, because obviously the side reaction lead to the consumption of the lithium, but also of the charge stored. Don't forget, never forget that the amount of charge stored in a lithium-ion cell depends on the amount of lithium stored into the cathode. So the more lithium and charge is consumed for the SCI formation, the less will be the capacity of the cell at the end. What are the properties? I mean, what we hope we get out of the SCI. So the first property, very important, is that it should be only permeable to lithium ion and have lithium ions and have a very high ionic conductivity, because we obviously want lithium to go through the SCI into and outside of the graphite. It should be ideally electronic insulating, because if this doesn't happen, the electrolyte will keep decomposing forever, and we will see that actually this is a problem for silicon. We will see later. It should have a very uniform morphology and chemical composition in order to guarantee an homogeneous current distribution through the whole electrode. If we have this homogeneous current distribution, then we will have hot spots, and this is definitely not good for performance, but also for safety. Very good mechanical strength and flexibility, allowing the expansion and contraction of the graphite and graphene lattices that occurs upon insertion and the insertion of lithium. And it should be not soluble, or at least have an extremely low solubility in the electrolyte, because if it dissolves, then it needs to be reformed again, and this will consume charge. So this picture, which gives us a pretty good idea of what is in the SEI, it's actually was made by Emmanuel Pellet in 1979. Most likely made the year before, because at that time it took more than a year to publish a manuscript. It was not that fast like it is now, but we are still more or less there. So the SEI, it's a layer which is a few hundred angstrom thick, so a few tens of nanometers. Okay, and it's a mixture of organic and inorganic components. I'm sorry, there is some overlapping. And the inorganic components are definitely very important. These are usually lithium oxide, lithium fluoride, lithium carbonate, which can be actually formed by the decomposition of both the salt anion as well as the solvents. And then there is also a certain fraction of organic components like semicarbonates or alkoxides. And there are also some polymeric components formed by the decomposition of the solvent, which actually altogether guarantee this optimal performance, which we see in commercial lithium-ion batteries. Okay. So the electrolyte itself has a very big role in the SEI formation. We know that electrolytes for lithium-ion batteries contains, I guess the next speaker will also talk about this, are usually mixture of high dielectric constant solvent and low viscosity solvents. And the reason is easy, obviously, because we want to optimize salt solubility, which is then given by the high dielectric constant solvents, with ion mobility, which is then guaranteed by the low viscosity solvents. We need to reduce the viscosity of the electrolyte in order to get good mobility. These are the most common: ethylene carbonate, propylene carbonate, dimethyl carbonate, ethylmethyl carbonate, and diethyl carbonates are the most commonly used solvents for lithium-ion batteries. Okay, high dielectric constant, low viscosity. Don't forget the Walden rule. In order to optimize conductivity, we need to have high salt concentration, but also low viscosity in the system. Okay, there is no perfect solvent which can do all the job. So if we consider the melting point, we want the battery to work at a very wide temperature range. Then DEC has the lowest melting point, so it's good from this regard. The EC, it is actually solid at room temperature, so it's not very good. But then if we look at the opposite, we don't want our solvent electrolyte to boil off very easily, then we have almost the reverse picture, okay? Dielectric constant also goes, it's very high for EC and very low for DEC, but if we look at the viscosity, then it is the opposite, and so on. So there is no perfect solvent for the electrolyte, and at the very end, there are some which are better than others, and they are usually combined together in order to optimize the overall performance. Talking about salts, at the very end, there have been many salts which have been investigated. My first lithium-ion battery I made about 30 years ago for a rechargeable hearing aid used lithium AsF6, which is an exceptionally good salt, but unfortunately it's too toxic. Lithium perchlorate, it's, for example, explosive when it's very dry, so it's very difficult to be used. And most of the proposed salts so far have some problems. They are either not conductive or toxic or explosive or corrosive and so on. So at the very end, the salt of choice is LiPF6. Okay, but for example, TFSI is commonly used as additive also into these electrolytes. And regarding the high dielectric constant solvent, EC is the preferred one because PC and GBL do not really form effective SCIs. For the low viscosity solvent, usually DEC, EMC, and EC are DEC are deselected, and then there is a multitude of electrolyte additives. I'm just listing a few here, but actually there are many more, and these are very confidential, which are also added. Okay, so but I guess the next speaker will give an even deeper overview on electrolytes. So I go back to graphite. Okay. So I mentioned that increasing the initial Coulombic efficiency, that means decreasing the amount of charge which is consumed to the formation of the SCI, is extremely important. And there have been several approaches in order to achieve this. One of them has been, for example, to coat or kind of pre-coat an SCI on an artificial SCI on graphite in order to limit as much as possible the consumption of charge during the SCI formation. And you see here that pre-coating of graphite actually can lead to better stability. You can also use materials for this pre-coating, materials which are stable at high temperature, and this would then result in better performance of the graphite electrode at high temperature. Another problem of graphite electrodes is especially when the cell is charged at very high current or very low temperature, it's lithium plating. I think I know that the group of the previous speaker, Margaret, demonstrated actually that lithium metal plating occurs almost always on lithium ion cells. This is acceptable up to certain levels. Nonetheless, whenever lithium plating occurs, lithium metal can react directly with the electrolyte, and this is leading then to low Coulombic efficiency, but also leading to safety concerns because we know that some spontaneous reaction can start and develop heat, and this would then end up with some dangerous failure of the cell. So lithium plating is definitely a serious problem, but also Coulombic efficiency. This is something that especially young people, they have always to keep it in mind, okay? So what I'm plotting here, it is actually the life expectation of a cell based on the Coulombic efficiency of the cell itself, okay? So very frequently, this is also a problem for my work as editor. Very frequently I receive manuscripts or I see manuscripts in which Coulombic efficiency in the order of 99% are reported. But please always consider that in order to have a decently working cell, lithium ion cell, or any kind of cell in which the ion is shuttled between two hosts, so there is no reservoir of the metal itself, the Coulombic efficiency, in order to get a decent life, has to be extremely high. I mean, you see here that even 99.9% Coulombic efficiency results in a very poor life. Decent Coulombic efficiency start to be above 99.99%. And in some cases with lithium ion batteries, even 99.995% are achieved, and this then can result in a cell life longer than 2000 cycles. Okay, so always keep in mind the extreme importance of Coulombic efficiency, which I think has been highlighted very well by Jeff Dunn with his accurate measurement system. Okay. So what is the future? I mean, with Margaret, we had the chance to organize one of the last meeting in person. Right now, we are always all getting used to talk in front of a computer, which I really don't like it. And which was even more amazing because Stanley Whittingham got actually the call announcing his Nobel Prize right after his presentation. This was really amazing. But anyway, at this ABA meeting, we kind of collected the inputs from several agencies like the German BMBF, but also the American DOE and Japanese NATO and the Chinese Academy on Science. We ask them, what is your, let's say, expectation about the future, okay? And the expectation about the future, as you can see in this graphs here, or in these pictures here, is that lithium-ion batteries, most likely lithium-ion, but maybe also lithium-metal batteries will lead the EV market for the next 10, 15 years, maybe even more. I mean, it's still not clear yet if there will be another technology replacing lithium-ion or lithium-metal batteries. So this makes it clear how good are lithium-ion batteries based on graphite produced so far, okay? And the point is that now on lithium-ion batteries, there is a big expectation about sales, okay? You see that it's the number of gigawatt hour produced in the next, or the increase in the next 10 years, it's definitely extremely important. And why is that? Well, one of the reasons is, this is one of the many studies made. I mean, the reason of this incredible growth expected in the transportation sector is simply the energy efficiency offered by lithium-ion batteries in vehicles compared with other systems. I mean, alternative systems like hydrogen or power to liquid approaches, okay? And this is also, I mean, this is not only scientific evidence in a sense, but it is also financial evidence. As a matter of fact, this is very well testified by these numbers, okay? These numbers are amazing because they are telling us that Tesla capitalized as much as Toyota plus all the large German car makers, and even a little bit more, in spite of Tesla selling only a very small fraction of cars that these 4 car makers altogether sell, okay? So, but clearly the fact that Tesla decided to go full electric, now also Volkswagen is going full electric, Toyota, I mean, all car makers are moving to full electric battery powered cars. Will certainly, the gap will be closed, but clearly, financially speaking, Tesla has been benefiting of this decision to go 100% electric since the beginning. And in fact, for example, if we look at the European market, at the last year numbers, so if we look at the whole here, which is the plot on the left, we see that actually hybrid and electric vehicle are growing. But what is even more impressive, if we look at the last quarter of 2020, hybrid plus electric vehicle reached almost 1/3 of the new sales, which is definitely impressive. I mean, diesel is more than diesel, and very soon it will approach also the gasoline cars. As I mentioned before, we expect this huge market increase in the lithium-ion batteries, and this is very good for all scientists and companies involved with batteries, but is also raising a kind of new problem with respect to sustainability. Okay, right now batteries are not very much sustainable systems. As we already heard from Margaret before, there are serious problems on the cathode, and we need to change the approach we have toward batteries. We need definitely to start working on the direct recycling of battery materials, rather than burning everything like it is done now. And we also have to start seriously thinking about design cells for recycling, okay? Which is definitely very important. So I mentioned that so far, most of batteries have been the recycling of batteries involved burning them first and then extracting only the precious metal like cobalt and nickel, maybe aluminum and copper. But for example, most of the lithium inside the cells is right now wasted. Okay, we definitely need to improve, and this is some work we have done in the past, for example, together with the company Recupil on the hydrometallurgical process to recover materials. I mean, there are full recycle approaches in which every single component can be recycled. This is not a big issue. What we have been working is just to stick with graphite is where within a couple of EU projects, MarsEV and SPICY, and Recupil developed a process to actually separate everything. And what I'm focusing today is on this carbon cake. Okay, so only the carbon fraction out of the whole of the crushed cells. Which is easy to extract, and which this is actually the graphite we could get out of these materials. So direct recycling of graphite, this is what I'm talking about. And we have actually demonstrated that this recycled graphite can be actually re-employed as it is without any kind of treatment for the making of new electrodes. So it is possible again to process them using the typical CMC SBR composition. And this slurry have appropriate rheology for coating. We can make new electrodes and actually test them. You see that depending, let's say, on the cell, we get different performances, but still we can get decent Coulombic efficiency, for example, with the generation 0 cells, and also that we can get good capacity out of these cells. So it's clear that it is possible to recycle graphite rather than burning it, and recycling, direct recycling of material, it's definitely extremely important for this. I see that my time is almost ending, so I will enter into the second part, which is there are alternative anode material for lithium-ion batteries, and many of them, silicon is definitely the most interesting because it offers much higher gravimetric and volumetric capacities than graphite. Nonetheless, the situation is not that easy now. This graph is extremely complicated. But what I want to show you actually is the reason why, in spite of capacity being very good, the reason why we still do not have pure silicon anodes. And this blue curve, okay? All of you know about this, but the volume of silicon upon the alloying of or storage uptaking of lithium increase enormously. And this is actually leading to what is well known as the pulverization of the silicon particles. So they tend to break because of the stress induced by the volume change. they tend to, the coating tend to delaminate, always because of this volume change, okay? And this is actually leading to poor cycling, as well as to, very important, electrolyte consumption. Why is that? Because obviously the pulverization breaks the SCI, creates new active surface, and then new SCI is reformed. And this on the long term is leading to large electrolyte consumption. So it has been demonstrated that if you go very small in the particle size, then you can have the lithiation without pulverization, which is okay. But this is obviously in introducing a very complex composite electrode preparation. You have a very large active material surface area, and this may then require a huge amount of charge for the formation of the SCI. So it is always a balance in the way we can go to solve the pulverization problem of silicon, this associated to the large volume change. Okay, there have been many approaches proposed. One of these is, for example, using polymer that can, binders that can self-heal. Actually, this is also one of the subjects of the important subjects in batteries 2030 plus, right? Self-healing batteries. These polymers have the ability to bind on the silicon particles even after pulverization, and kind of keep them together, preventing the at least the mechanical degradation. There are also more fancy, I call them fancy. These are highly engineered composites in which very tiny nanoparticles of silicon are deposited on or in or within three-dimensional structures. These are amazing materials. Good cycle performance has been demonstrated, but always do not forget that whenever you introduce an additional component, and especially with these three-dimensional electrodes, the overall performance at the end might be lower than even than graphite, conventional graphite electrode. So never forget what is the real reference material, which is graphite. However, a good approach, and just to go back and talk about graphite again, a good approach has been found to kind of disperse silicon nanoparticles in combination with graphite, okay? Because in a sense, the SCI forming on the graphite material, it's also including the silicon particles. Silicon nanoparticles are very small, so they don't break too much. And this is is an approach that actually led to pretty stable, let's say, composite electrodes containing silicon up to maybe 7 to 10%. So far, it's demonstrated 7%, I think, is the highest in commercial cell. And actually, this is more than enough, because we should never forget that it is not that useful to enormously increase the capacity, the specific capacity of one electrode, if the capacity of the other electrode is very low. So if you're looking at this graph, for example, here, you see that the increased anode specific capacity does not really result in an increased cell capacity when you use, for example, a low capacity cathode like lithium cobalt oxide. But obviously, the more you increase the capacity of the cathode, these are kind of theoretical estimation here for oxygen and sulfur, the more you benefit also of the increased capacity from the anode side. So increasing a little bit the capacity of the anode is definitely good already, for example, for the lithium rich or lithium and manganese rich oxide cathodes. But we don't really need to go very high. Silicon oxide as itself or in combination with graphite in composites is definitely an interesting material. However, because it takes advantage of the lithium oxide matrix, which is formed during the first lithiation. It's extremely interesting actually for commercial cells. On the other end, the fact that we have to transform the oxygen into the lithium oxide, this requires consumption of lithium. And again, don't forget that in a conventional lithium ion cell, all the lithium comes from the cathode. So there are a lot of activities actually now going on about the pre-lithiation, which is something extremely important. So in the sense that you add more lithium into the cell and to avoid the cell performance lost due to the consumption of lithium during the formation. And this is actually done in several ways. There could be the use of a sacrificial lithium metal electrode inside the cell, as well as the addition of lithium powder during the cell assembly, for example, depositing lithium powder on the separator or on top of the negative electrode, as it is indicated in the slide. I think my time is over. I would like to leave a little bit of time for questions, so I will actually stop here. And thank you for your attention.
Thank you so much, Stefano. Thanks a lot, and I think many people get interested in your talk, as we have many questions actually. So I'll try to go through hopefully some of them or most of them. So the first one will be, what is your opinion about the future of other anode materials like LTO, which are safer than graphite, even though they provide less energy?
I mean, these materials can obviously find niche applications. Okay, LTO, it's definitely LTO anodes are safer than graphite anodes, but they have much less capacity. Maybe they can provide larger power. So for a very specific application, they can certainly be used, but nonetheless, graphite still is the material of choice when you are talking about high energy storage performance. Okay.
Yes. Okay. And there are actually several questions regarding recycling. Some of them are like, other than electrochemical performance comparison, what are other characterization techniques that can be used to compare recycled graphite and pristine graphite?
I'm sorry, I didn't catch the question.
Somebody's asking, other than the performances, how can we characterize recycled versus pristine graphite?
It's exactly the same approach at the very end. I mean, I showed some old results. Right now we have much better results, but these are still unpublished. And what we get this recycled graphite from commercial batteries, and then usually you need some thermal treatment to get rid of the carbon black, because otherwise the irreversible capacity in the first cycle is too high. But then it's typical. I mean, you can make the very standard characterization, which is done for the fresh graphite, nothing different. And the performance, it's actually amazing. It's almost more or less the same. The same applies also for cathodes. I've seen a presentation last week given by a guy from University of California in San Diego, and it's amazing. I mean, it was capable of recycling the positive electrodes, which is definitely something we should take.
Yes.
Consider very seriously.
And there is another question regarding the price of recycled graphite. Do you believe it's going to be cheaper or?
Yeah, because you don't have to produce it. I mean, you only need to separate it and just do a simple thermal treatment. As I said, the only problem in the recycling process is that usually the conductive carbon additive, which is in the cathode, ends up being with the graphite at the end of the process. Okay, the recycling process. And this is a little bit of a problem because it contributes to the irreversible capacity in the first cycle. This needs to be eliminated, but can be done just by heating. I mean, for the rest, even the shape of the graphite is not strongly affected. You can just reuse the same material as it is.
Yeah. Another question regarding your opinion about lithium metal batteries for the next generation of liquid electrolytes. Do you think it's going to work? I guess that's the question.
It depends what is, I mean, right now, most of the efforts are going towards solid electrolyte for lithium metal batteries. Historically, I'm working with ionic liquid, so we do have cells that can cycle lithium metal for many cycles, but ionic liquids are still somehow limited in terms of conductivity. So to achieve very high rates is still a little bit of a problem. But we need to keep investigating and make further progresses. But I think it's going to be a kind of hybrid solution at the very end. Solid state electrolyte with some kind of liquid interlayer between the lithium metal and the solid state electrolyte.
Okay. There is another question regarding the pre-lithiation strategy, and especially for industrial application. The question is to know what is the effects on the energy density and the cost per kilowatt-hour, and to know if pre-lithiated silicon oxides are more favorable than graphite.
Well, that's always a balance, I guess. It becomes more engineering than chemistry. So I mean, if we really enter into the engineering details, I don't feel comfortable to express opinions. Okay, but engineers can do very well. So and pre-lithiation strategies are definitely, especially if we want to go higher with silicon, we need to introduce them. That's my feeling.
Yes. And I think I will take one last very quick question. It's regarding that point. What is, in your opinion, the most promising strategy to implement high silicon content in commercial anodes?
This question should go to the previous speaker, actually, because Margaret knows much more than me on this subject. I don't know. Margaret, are you still in? Oh, maybe she's not.
Yes, yes, yeah. I'm in, but
okay.
Please, can you repeat
your
the
opinion,
question?
Please.
Can you repeat the question, please?
What is, in your opinion, the most promising strategy to implement high silicon content in commercial anodes?
High silicon, high silicon content. This is very difficult. This is very difficult to tell. But I think that the most promising thing is to use not so very sophisticated materials, for there will be in the long term they will be too expensive. To look for something with internal porosity, but what we need is also higher density also, and then some flexible protection. Is this?
Okay.
So engineered composites,
yes, engineered composite with,
but not too fancy, right?
Yes.
Okay.
I think
yeah.
I think it's a good summary that chemistry should always go hand in hand with engineering at the end. That's a very important point. Anyway, thanks again. We won't have time to answer all the questions, but let's thank Stefano once again, even though nobody can clap again. And so I would like to thank you. And we're going to move on to the next speaker.
Yeah. I'm sorry for the presentation not working properly. I don't know what is from. Okay.
At the end, it
That's
worked.
all right.
Very good.
Thank you very much, Stefan and Margaret, again. And so now we are welcoming Rongying Ling, which she will speak us about electrolytes. That's the topic, and she's a well-known researcher, and she obtained her degree in applied chemistry from the National University in Singapore in 2005, so she's very young. And she obtained her full Erasmus Mundus scholarship for Master in Materials and Energy Storage and Conversion program in 2008. So her PhD was under an industrial scholarship between Solvionic and CIRMAT, and she is focusing since that period and today on ionic liquids, electrolyte for supercapacitor application at that time. And then she got a postdoc in research on cathode materials for sodium-ion batteries. She joined Solvionic in 2013, managing European project and B2B collaboration. Currently, she's leading the energy storage team in Solvionic for European projects, and also the expansion of Solvionic in Asia and Singapore, of course. So we are very glad to have her here. And she will speak, she will tell us something about Solvionic. I want to also to add that we really wanted to get also someone from companies that will be very important for supporting the activities on lithium-ion production here. So she will give us a lecture on electrolyte, liquid electrolytes, and interfaces with the electrodes. Thank you very much, Rongying, for being here, and the floor is yours.
Thank you, Sylvia, for the introduction. So just a voice test. Can you all hear me clearly?
Yes, yes, I can hear you very well, perfectly.
Okay, so I will start to share my screen.
Okay, now we can see also your screen. And no, we cannot see the presentation mode. You should change the screen. We are seeing the other screen, maybe. I don't know how, but because we see, you know.
This way?
Yeah, yes, now it's perfect. Thank you.
Okay.
Thank you.
Thank you. So, yeah. Thank you, Sylvia. So today, I'm working in Solvionic now, and today I'm going to talk about electrolytes. I'll give a bit of introduction of the company, and then I'll go on to talk about liquid electrolytes and the interfaces with electrodes. So this is the outline of today's talk. So we will have an overview of the company, our technology, the production roadmap, and also the research development innovation roadmap. And the second part of the presentation, I'll give a brief introduction of what are the kind of liquid electrolytes that we are focusing on, and some influence of different liquid electrolytes and the components on the electrode and their interfaces. Then we will see what are the challenges we are facing now, and then we will bring you to the overview of how industrialization is coming about and changing in Solvionic. So Solvionic is a company that specializes in the production of ionic liquids, especially in high performance and non-flammable electrolytes. Right now we are expanding. We are moving next week, in 2 weeks, to a new site. And to the last year until this year, we have grown over 50%. So now we are still employing over to 24 people. So we are a very small company. Just a bit of history. Solvionic is created in 2003 by Dr. Francois Malbosc. He is the CEO and founder of Solvionic. And then first scale-up unit with quality control procedures was set up in 2004. Then we had a first expansion, which is R&D dominant. in 2007. Following that, in 2016, we had a second expansion, which is where I am presenting from now. And then in 2019, we had the first roundtable, meaning we asked for investments, and we have received 2.5 million euros. And so last year, as status quo from last year, we have 85% of international sales, 70% of them are industry. And right now, our capacity is 200 kilograms per month, and we have the highest quality grade of ionic liquids. So our main markets are, right now, major is like 60 or more than 70% of our main market is on electrochemical devices, and then followed by surface treatments, coatings, solvents, separation, and extractions. This is our product portfolio, where we have a range of over 200 references of ionic liquids, metal salts, and electrolytes. So just a brief introduction of what are ionic liquids. They are molten salts at low temperature. So as you can see here, they have very large organic structure that is asymmetric. So usually we have a short chain and then a long chain that makes them asymmetric, followed by organic or inorganic anion that is smaller. Because of this discrepancy in size, they have a low tendency to crystallize, and that's why they stay molten at low temperatures, that is, which is to say below 100 degrees Celsius. The electrochemical applications of ionic liquids, that is important. The properties that are important for the electrochemical applications are that they have very low vapor pressure. So you can see that in batteries, sometimes we have swelling and a bit of, that leads to explosion and stuff like this. It's because there is a gas pressure buildup, which later I will talk more about in one of the case studies. And then it is also non-volatile, so non-flammable, and they have very high flash points of more than 100, 200 degrees. They have a very large liquid range. Of course, when you talk about ionic liquid, they usually is about, you can have about -5 to 100, 120 degrees. But when you can mix them, which is very studied by, extensively studied by Professor Passerini's group, where they have eutectic mixtures of ionic liquids, you can also extend the liquidus range to -80. Ionic liquids, they have reasonably good ionic conductivity, up to 60 millisiemens per centimeter. And then they have very good electrochemical stability, up to 6 volts. Of course, here good ionic conductivity is relative. For example, if you have very good conductivity, you might have compromise also maybe on the electrochemical stability. So a lot of pairing is to be done. So we have many structural variations that gives us the ability to tune the properties. And also we can produce very good high quality products, which gives good device performances. So our specific know-how which we keep it as secret of the company, is on the ionic liquid synthesis process. So each chemical pathways are specifically developed for industrialization in such a way that is easy upscaling, and we take into a very serious consideration on the safety, toxicity, and to comply with the REACH regulations. We also have a specific know-how on purification processes that leads to very highly pure products. We have also very stringent ionic liquid quality control. So we have special modified analysis methods that can detect ionic impurities in ionic media, because Ionic liquids, they are very different class of chemicals. So they are different from carbonates, different from other chemicals. And so their analysis to detect them correctly, we have to also adapt the analysis methods to the analysis to find out about the impurities level. So we have today our level of impurities we can achieve down to less than 5 ppm of water level, less than 1 ppm of halides, and less than 10 ppm of amines. So this leads to very high performance electrolytes for batteries and supercaps. So to support our customers in the production roadmap, like what previous speaker has spoken about the growth in the market. So we are seeing the growth, we are having a lot of demand. So in order to support our customers, we are also growing and catering to this demand. So from 2020, where I left you just now with 200 kilogram per month capacity, and by 2021, we are currently setting up the new site that is housing a pilot plant that can produce 1.5 tons per month of high quality ionic liquids. And this pilot plant is not using the batch synthesis method, because previously, right now in the this site, we are still using batch synthesis, which is like 10 liters, 20 liters reactors. And now for the new pilot line, it will be on an intensive continuous flow method, synthesis method, which the reactors are much smaller, but we have a continuous reaction and continuous production. And by 2023, it is planned to install the first industrial production line, which will provide 4 tons of ionic liquids per month. And apart from production with innovation, with innovative technology, on the research R&D side, we have also to support our customers in developing their products. So in 2020, we have seen a lot of Gen 0 ionic liquid-based electrolytes, and then we help and accompany our clients to improve and to bring value add to their electrolytes. And so we will also adapt to their different generation batteries. There are different generation products. So for example, in generation 1, generation 2, and then generation X, through B2B and H2020 collaborations. This is a slide that was shown by Professor Edstrom earlier on the Battery2030, and Slovenia we are listed as one of the battery material supplier. So our current H2020 collaborations, we have C-Drive. C-Drive is focused on silicon nanowire as anodes and LMNO electrodes for and NMC electrodes as cathodes for highly performant EV batteries, and also ionic liquid electrolytes. The TRL level, TRL is the technology readiness level. So usually 1 to 3 is more on fundamental research, and then 3 to 5 where is more testings and more advanced research, and then where you can bring it to the prototype level. So beyond TRL6, we will have a prototype in the project, and then TRL 7, 8, 9 is towards the commercialization, with the TRL 9 being the product being commercialized. So here we have C-Drive, which is TRL 3 to 5, and then we have a couple of projects here, Cobra, Sense, and Hydra. They are also focusing on advanced lithium-ion cells towards the liquid and also solid-state batteries, solid-state electrolytes. And so here we are at TRL 3 to TRL 6 with a prototype, And this the aim is to produce between 12 to 30 ampere hour cells. Lastly, we have Solidify. It's a project that focuses on all solid-state batteries with lithium metal, and same is from TRL3 to TRL6. And to continue supporting our customer technology through the collaborations with H2020, we are also testing materials from customers on their materials such as NMC 622, LFP, lithium-rich NMC, graphite, and lithium metal. And in the future generations will also be other types of NMC, such as nickel-rich 811, LMNO, silicon graphite, low silicon content, as well as high silicon content, which is we are seeing a growing number of companies engaging in such the development of high silicon content anodes, and also developing technologies with on lithium metal. Of course, we must not forget about additives, because additives, they are very important in our electrolytes. And then we are also developing gel and polymer solid electrolyte, especially for lithium metal technologies. So now I will go to the second part of our presentation on liquid electrolytes. So here is a very simple model of lithium-ion cell. So you can see that there's the aluminum current collector, the cathode, the separator, the anode, and then the copper current collector. And of course, here we can see the electrolyte is impregnated in the separator, but this is a simplistic model. So you have to keep in mind that when the electrolyte is liquid, it goes everywhere, literally everywhere. So in this sense, we have to keep in mind that although liquid electrolyte has a lot of benefits, it can also create a lot of challenges. So for electrolyte, we have classifying them mainly into three categories: liquid, gel, and solid. And so today the focus will be on liquid electrolytes. So mainly in liquid electrolytes, we have salt or salts, different salts. We can have one solvent or a couple of solvents, and then a lot of additives. So you can imagine the number of permutations that we can do. And these electrolytes, they are, I mean, more often than not, I mean, time to time, there are some clients, they send email and then they will say, give me your bestseller electrolyte. So, and this is difficult to explain, because to them, when they are not into this, especially through industry, sometimes it can be, I mean, we have different types of clients. So sometimes it's important to stress that it depends on the materials they are using. So today, I'm going to talk about mainly the different types of solvents that we can use, and also the effect of additives, different solvents, or even salts that can have an impact on the interfaces of different electrodes. The important properties of electrolyte are their conductivity and viscosity, because this will directly give them translate into the desired performance. So if you have good conductivity, low viscosity, then we can have more powerful devices. Then the thermal stability is important, because then you can use the battery in a large temperature range, especially when today we have batteries will be used in the North Pole, and then very hot climate or very harsh conditions, such as, or even very niche markets where in drilling, because in drilling we need to, the temperatures are more than 100, 200 degrees. So it's important to have thermal stability in the electrolytes. For for the device to work. Another important property is the lithium transport properties, where is the ability of lithium to move around within the electrolyte. So this will translate into efficiency of the device, like what was discussed earlier on Coulombic efficiency and all this. So, and then the next one would be on electrochemical stability. This is very sought after because when we have increased electrochemical stability, we have high energy, because energy is directly proportional to voltage. So, which is why people are also looking at ionic liquids, because of the high electrochemical stability. And also very important as we are having more battery users, and the performance limits, they are pushing to the limits of the material. So so when the carbonates are being pushed to the limits, more often than not, we have consequences, which I will show later. And so low flammability is very important, and because we need to feel safe when we use the batteries. So here for the liquid electrolyte, basically we have salt, solvent, and additive, and we can classify them into aqueous and non-aqueous. So with aqueous systems, we have them in the cars, lead acid battery, and other batteries are the multivalent batteries such as zinc, magnesium, calcium, aluminum, and we also have alkaline metal salts that works on sodium chloride, KCl, and so on. Then today I will focus on the non-aqueous electrolytes, solvents. So mainly, today we are mainly using carbonates, and has been, the commercial batteries are mainly using carbonates. And then we have also another class of solvents that are getting very popular. Also, they are the polyethers. And then lastly, the ionic liquids, which I previously presented. So here are the structures. And for ionic liquids, here are the three main functional groups that we talk about. And also there's another group that is getting interesting as well, which is the phosphonium. So there's the imidazolium here, and then the pyrrolidinium and the ammonium. And each of them gives different stability and different types of, different level of ionic conductivity. So depending on the applications, different ionic liquids will be required. So for the commercial electrolytes, today most of the commercial electrolytes are using LiPF6 as salts, and carbonates as solvents, and SCI forming additives. As previously mentioned in the previous speaker slides, also here is a list of carbonates that are commonly used now in the commercial electrolytes. And basically there are two types of carbonates. So we have the cyclic ones and then the linear ones. And the important properties are the flash points and like dielectric constant. And we can see here that they have very, very low flash points that sometimes lead to safety concerns. So why do batteries explode? Because we have seen like some couple of Tesla that has exploded and caught fire, and the Samsung Galaxy Note 7 back a few years back, there was a huge recall and lots of money lost due to the safety of the batteries. And then we have also accidents in electronic cigarettes. So the possible causes of the explosion are usually due to the flammability of the carbonates. They are unstable at high voltage as we charge to higher and higher voltage, the limits are being stretched. So it's easy to have a thermal runaway, and then leads to heating of the cell and eventually fire. And also the LiPF6. Today, when we test the electrolytes, the batteries, we seldom go beyond 40 or 45 degrees when we use LiPF6 or carbonates, because LiPF6 salt is thermally unstable above 55 degrees Celsius. And beyond that, we risk the production of toxic gases, and the PF6 also can decompose to HF in the presence of water. So there are some solutions at the moment, that is adding some flame retardants, additives, or we can use improved BMS to control. But these solutions can be costly and can also contribute to inactive mass within the cell. There are other electrolytes that are becoming popular, and I would say commercialized. One of them is ionic liquids. So they are already being used in batteries that are commercialized. And so this is an example of EMI, the TFSI anion and the FSI anion. And then this is the pyridinium cation and the piperidinium cation. So these are the examples of ionic liquids that you can see. The reason why ionic liquids, when we use ionic liquids or carbonates, we need additives, and especially for ionic liquids, as you can see here on the figure on the right, here is the current density versus the voltage, and this is a typical graph of stability window. So applying linear step voltammetry, so we can see, we can measure the window stability. So here you can see that the carbonates, they have a shorter window than most of the ionic liquids. So, and the SEI has been formed due to partial decomposition of carbonates. So without the presence of carbonates, the ionic liquids, they are very stable. So they cannot, they don't decompose to form the stable SEI layer to allow the efficient transfer of charge. So in this sense, additives are very important when we use ionic liquids. Of course, this is very subjective to again, the electrolytes. For example, if you look at graphite, we absolutely need additives. But if we look at examples such as LTO, then sometimes we don't really need additives. So it really depends on application and the material. Then we have the glimes. They are called polyethers. They also called glimes. Here we have, I show a range of glimes. So basically we call them monoglyme, diglyme, triglyme, and tetraglyme. And for the glimes, they are, we have to be careful when using glimes because especially monoglyme is flammable and toxic, and it has a very low flash point of -6 degrees Celsius. It is widely tested and used in lithium metal or lithium ion batteries. So I will talk a bit more about the polyethers, the glimes. They're interesting because they have very low viscosity and they have good conductivity and high boiling point. If we don't talk about monoglyme, starting from diglyme, triglyme, and tetraglyme, we have good boiling points. And however, they have medium electrochemical stability, which is around 4 volts. The very commonly used studied glyme is the tetraglyme. And this tetraglyme, if you look it up on this website, which is the European Chemicals Agency website, we see that it is very toxic, and the description here says may damage fertility or the unborn child. So we also have to be careful when using glynes. And in this aspect, Solvonic also we try to make it less toxic, and by substituting the N chains, the end group of the chains to non-methyl group, such that to reduce the toxicity level. So how does it render the glyne toxic? So first, when it's monoglyne, it is toxic. And secondly, it's when the terminal groups are methyl. So if we change it to ethyl here, then the toxicity level reduces. And now I will move on to the additives. Additives are both for SEI on the anode side and as well as the ZEI on the cathode side. And it's important in the formation step. So what is the solid electrolyte interface? I think just now we have quite a very good explanation. So I will just stress on the points. So it's to block the direct contact of electrons with electrolytes, and it has to be a good ionic conductor that allows lithium to pass through, and lithium ions to pass through, chemically stable, mechanically stable, and it has to be thin, so that the resistance, to keep the contact resistance low. And like what I mentioned, that when using ionic liquids, more often than not, we need additives, because we need additives to stabilize the SEI layer. So these are the some of the examples of the additives. Very commonly used are the VC, the FEC, Liebherb. Recently, very much discussed is the succinic anhydride, as well as the trimethyl silyl phosphide, which also termed the TMSP. When we talk about electrolytes and interfaces, it's very important to look through the whole stack components, especially when the electrolyte is liquid. We have to look at interactions with the current collectors. So different electrolytes will react differently with different current collectors, like aluminum, copper, or carbon-coated aluminum. I mean, even if it's stable with aluminum, and when there's a carbon coating, we know that carbon, they can have a lot of functional groups depending on the activation processes. And so this can also decompose, results in the early decomposition of the electrolytes. And then you have also like reaction with nickel and so on. On the anode side, we have to also test the stability with the graphite. The same electrolyte that work with graphite might not work well with lithium metal, same as this silicon, pure silicon, as well as silicon graphite, LTO, and so on. The other challenge is also we have to look into the interface between separators, because sometimes the interface even between cathode and separators with electrolytes, sometimes it just doesn't match. So here we have to look at different materials, affinity with the electrolytes. Basically cellulose plus fiber, there's not much a problem. But when it comes to ionic liquids, the polyolefin based ones, it can be a challenge to wet them. So also followed by, we also have other separators that work well. However, separators are important, but when we deal with research to industrialization, it's a different. It is very important to use separators that can be easily industrialized. For example, we need ceramic, but ceramic that will not crack easily. And this is important, especially when we roll the cell or when we stack cells in pouch cells. So these are a lot of things that we have to consider, bringing solutions to our customers. And also on the cathode side, there can also be dissolution of metals into the electrolytes. A lot of factors can affect. So interfaces need to be studied for each type of each pair of electrode and electrolyte. So we have LFP. We have also studied extensively NMC 111, 622, 811, LMNO, and NCA. All these, they have different reactivity to different electrolytes and additives. So there's a lot of things to consider. So in the following slides, I will speak a bit about the different interfaces that we see when we pair carbonates with graphite, with even different carbonates, and then the structural effect of lime into graphite, and then the performance of some limes in NMC, and also carbonates with LMO, ionic liquids with LMO, and then with silicon graphite. And then lastly, the last case study on additives. So in this case study, we look at this is a half cell that is built with lithium foil disc and graphite electrodes with a loading of 1.4 milliamp hour per square centimeter with a Wattman glass fiber separator. So with the in situ X-ray diffraction in this electrolyte of ECDMC with LiPF6, we see that in the absence of PC, we can see the lithiation of graphite. And here, the different colors of the arrows correspond to the different peaks that we see on the X-ray diffraction, showing a gradual lithiation of the graphite. And here we can see in the SEM picture that there is no exfoliation of the graphite. But however, once PC was introduced into the electrolyte, we can see that there's a plateau form at about 0.9 volts, and there is no observation of lithiation. And here from the SEM picture, we see an exfoliation of the graphite material. So of course, we now it's quite well known that graphite and PC, they are not good friends. And so additives are very important. And usually with graphite, the first additives that we will add will be PC, for example. And so now I move on to diglyme and graphite. So this is a paper that showed that with the lithium salt and the diglyme, there is an intercalation, co-intercalation of the linear diglyme into the graphite layers. So when we look at the voltage versus capacity profile of the lithium salt in diglyme and the lithium salt in ECDMC, we see that in ECDMC, we have a good capacity, specific capacity. And when the solvent is being changed to diglyme, it seems like there's a huge hysteresis, and also the capacity is limited here. And this is due to the co-intercalation of the linear diglyme into graphite layers. However, but if we change the structure of the diglyme, okay, so in this paper, they show two different types of glyme. So either we can have a monoglyme or a diglyme, and then the R group on the left can be a methyl group or an ethyl group. And so when the glyme is branched, here we can see on the right, it's a branched molecule as compared to being linear. They have they are considered also as hindered glymes. In this paper, they call it hindered glymes. And when these hindered glymes are used, we can see here on the figure on the right that the discharge capacity actually improve. And by changing the structure, we prevent the co-intercalation of the glyme into the graphite structures. And here is a table of the properties of the physical properties of the electrolytes. So here they use LiFSI as a salt. So there have been a lot of studies with LiTFSI and LiFSI in ionic liquids as well as lines in lithium-ion batteries as well as sodium-ion batteries.
So we have just a few minutes, please.
Oh,
so we have time for questions. Okay. Thank you.
Okay. So in the end, so then we also, this paper also talk about the variation of different concentrations. And we can see that here the performance is much better than LP30. And these unsymmetric limes, they are compatible with a lot of materials. And this is another example. This is a paper that is published by Siliong, which is now acquired by Tesla. They also tested the lithium manganese rich oxides into carbonates and purely ionic liquids electrolytes. And we can see that there is a huge loss of capacity when carbonates are being used, and when there's ionic liquids, the capacity are much better. And this is due to the transition metal dissolution. This change due to interactions with carbonate electrolytes. And so the ionic liquid-based electrolytes, they improve the interface, enhancing capacity retention. And this is how good the cycling is with pure ionic liquids in a half cell. And this is with the full cell with silicon nanowires. And this is the last example on the additives. So here we have TMSPI and TSPA. So these additives, they have been studied using online electrochemical mass spectroscopy. And by detecting the gas evolution of O2, CO2, and POF3 and Me3SF, we can know the extent of the formation, the effect of the additives on the formation step. So this is an NMC full cell with graphite. So they have FEC-DEC and EC-DEC, and we can see that with the two main producing gas are POF and Me3SIF. We can see that there is a suppression of the electrolyte. The electrolytes, they do not produce, when the additives are used, they do not produce these two gases that can be detrimental to the cell performance. And the reactivity of different of the additives are actually different in different types of carbonates. For example, it's much higher in FEC than in EC. In EC than in FEC containing electrolytes. So I will skip. So right now, all these new interfacial chemistries in material compatibility, performance, and processability, we are working closely with clients through B2B collaborations and also Horizon 2020 projects. So the choice of electrolytes, to sum it up, is very dependent on each and every component of even your electrodes. So the active material, binder, conducting carbons, additives, on the binder side, whether it's SBR, cellulose, PVDF, HFP, even the process, such as whether it is done by, prepared by aqueous or organic, the surface is different, the interface is different. And also on the metrics, the loading is important. If your loading is high, then we have to think about the conductivity or the viscosity of the electrolyte, the thickness, the treatment, whether it's calended or not calended, also have an effect on the electrodes, on electrolytes. And also the availability of the raw materials, that brings us to the cost, the manufacturability, and of course, whether it's industrializable. So this is very important that right now we have very close collaborations with the different partners in Europe under the Battery 2030 Plus, where we have, and also Horizon 2020, where we have all these collaborations, where they offer us a toolbox of different interfacial studies methods such as XPS, SEM, NMR, in operando, in situ, process of cycling to gather the data so that we can analyze and improve on our material and our formulation of electrolytes. And also in post-mortem and gas evolution, these are important data that we need to bring about incremental improvement for our clients. And then also supported by modeling to know how we can improve. And this testing also is important because protocols are important for different interface. The analysis and also the formation is very different. And this also provides us with new materials to test to be abreast of the technology. And then this will bring us to prototyping and demonstrators, which is very important in an industrial point of view. So about the processability and the reliability and quality and sustainability and cost, Solvay Ling is working on it, and we are expanding, and this production line is easily duplicable. In 6 months, we can build a plant. And since we are producing 4 tons per month, we're going to generate a lot of waste and energy. So our technology also will look into the reduction of waste and the recyclability of the waste, and the sustainability of ionic liquids is also being studied. We are also looking at the recycling of ionic liquids, which now we think that it is possible to recycle up to 70%. And we are also looking at the second use of the ionic liquids, such as for lubricants, where they don't need such high quality. And we put importance and focus on the circular economy of our products and the waste generated. So having prototypes and demonstrators are very important for us. And so with this, we also we are happy that there's a network like the Ally Planet, where a lot of pilot lines are being built so that we can actually have more B2B collaborations easily. However, I feel that if there can be a platform of pilot lines being where the pilot lines can be even close to each other, and to have the different components in the value chain that can bring to TRL 8 or 9, that would be even better. And I think we are moving towards there, and so we need to have a stand in the global market through the pilot line demonstrators, and not only by the industry alone, but with different industries side by side. And this initiative will really help to enhance the collaborations within the battery manufacturing value chain as well as the end users. So this is the conclusion. Basically, we have looked at different electrode interfaces with the different materials, and then the importance of the properties and the impact of their performances. And we talk about importance of interfacial techniques and testings, that this is a toolbox that will allow us to know more about our materials, and then to continue to move on to prototyping and to create demonstrators. And that pilot plant platform, I think we are moving towards, but it will be really good for advanced B2B collaborations. Yeah.
Thank you very much, Rongying, for the very nice talk. We have a lot of questions. As we are a little bit delayed, I will just ask you a couple of them. And then even if we are a bit longer, we will finish on time for lunchtime. So just one question is, how can you, thank you for your talk. How can we improve electrolyte wettability with super concentrated ionic liquids or ionic liquids with polyphene separators?
Well, yeah, if we can improve
the electrolyte wettability with super concentrated ionic liquids with polyolefin separators?
I think if we use ionic liquids, then I think it's difficult to wet it, even with the salt. Personally, I've not tried, so it can be a good direction, but with polyolefin, it's really difficult. The moment you just put a drop and the drop just forms a ball there. Yeah.
Can we ever expect good liquid electrolytes with 5-volt stability? What would they be based on that would enable many new high energy cathode materials, of course, if we can reach 5 volts?
Yes, we can reach 5 volts, and we have already reached 5 volts with ionic liquids. Purely, okay, with 5 volts, you can do it with pure ionic liquids. However, the C rate will be compromised. So there's always a need to mix, and the amount of the composition must be optimized such that we don't compromise so much on the voltage and the performance on the cyclability.
Very good news. So there's also an interesting question. In average, which is the difference of cost between ionic liquids and common organic electrolytes nowadays? And how this will change with the creation of new continuous process plants?
I like this question a lot. Okay, so right now, the carbonate electrolytes, they're very cheap. They can cost less than $10 per kg. And if you look at the ionic liquids, they are from our catalogs. If you buy off the catalogs, they are like you can have 1,000 euros per kg. Okay, that's a big difference in the cost. But this is for research scale. But when we go to industrialized cost, we can actually reduce it to 50 euros per kilogram. But of course, it's still high. But if you look at the amount of energy that we can bring, if you don't look at per kilogram, but if you look at per unit energy stored, then we are competitive. Ionic liquids can be competitive in terms of price. And not only this, because right now we can see that when we take the planes or when we transport batteries, there is always this, okay, you have to declare, you can bring it on board because they are hazards. So with ionic liquids, it comes with it the security that we don't have to pay the price for it. So all this comes into play, and this is only what we see now. But if in the future, when we recycle ionic liquids, the revenues generated from recycling of ionic liquids will be able to push the cost even lower. So it really depends on the extent of sustainability, how we put efforts into gaining to make it the quality better and the cost lower, and also the industrial process of making the FSI anion has also gone down. So that's why we are also pushing for the use of FSI, because it's going to be cheaper. Also, it has very good SCI forming effect. So yeah, so basically the cost, we can't just look at the kg, but we also have to look at the energy unit stored.
Okay, very quickly, as you were citing the last question, and then I apologize with those I didn't ask it. Could you please comment on the influence of a coating on cathode NMC particles on the SCI? And do you may investigate with different type of electrolytes of course?
Okay, the cathode materials, it depends on, yeah, it really depends, because we see a lot of transition metal dissolution, and we don't even need to test them. We just soak them into electrolytes, and tomorrow we see that it's purple color. So the coating is important, but it must not add to it must not contribute to the early decomposition of the electrolyte, and it must contribute to a constructive and thin CI layer.
Okay, thank you very much, Rongying. So now we can take 10 minutes break. I just ask you all, Margaret and Stefano, if you are still here, and Irace, if you can turn your camera on, we can take a picture. So we keep it if you can. Thank you, Stefano. Irace, are you also here? Oh, great. And Margaret. So we just take a picture, just smile, please. Just for future. Thank you very much. But you know, now life is public, and so we need to. Thank you so much. Thank you also for being with us. We take a 10 minutes break, and then Irace, the floor will be yours. Thank you. See you in a while.
Thank you.